Hi, my name is Suresh Pillai and I work for Institute of Technology Sligo, situated in the beautiful west coast of Ireland. My research is mainly focused in the area of advanced functional materials and nanotechnology. Developing materials for energy and environmental applications are the major research activities of my group. Currently, I'm working with my US and Northern Ireland collaborators to develop visible light active photocatalysts. This program is supported by Science Foundation Ireland as part of the US Ireland R&D partnership. Before going into further details, let us discuss what photocatalysis really means. Photocatalysis is a process in which acceleration of a reaction occurs when a material, usually a semiconductor, interacts with light of sufficient energy to produce reactive oxidation species or ROS. These ROS can degrade organic pollutants into simple molecules, for example, carbon dioxide and water. When light energy greater than the band gap energy hits semiconductors such as titanium dioxide, electron from the valence band will be moved to the conduction band. In the case of anodized form of titanium dioxide, the band gap is 3.2 electron volt. Therefore, UV light or ultraviolet light is required to initiate the photocatalytic reaction. The absorption of a photon from the ultraviolet light excites an electron to the conduction band, which generates a positive hole in the valence band. Electrons in the conduction band can react with molecular oxygen to form superoxide radical anion. The superoxide radical anions can be further transformed into singlet oxygen. Hydroxyl radicals and superoxide anions produced by the photocatalytic process can degrade the majority of organic compounds until the complete mineralization is achieved. The main limitation for the industrial application of photocatalysis is its wide band gap. For example, in the case of anodized TiO2, the band gap is 3.2 electron volt. This means that photons of light in the ultraviolet region only can initiate the photocatalysis reaction. As we know, ultraviolet light makes up approximately 5% of the solar spectrum, whereas almost 40% of the solar photons are in the visible region. Therefore, in order to enhance the efficiency of TiO2 under solar irradiation, it is necessary to modify the band gap to facilitate visible light absorption. Non-metal doping of titanium dioxide has shown great promise in achieving visible light active photocatalysis, with nitrogen being the most promising dopant. Incorporation of nitrogen into titanium dioxide lattice is favored due to the comparable atomic size of nitrogen and oxygen, low ionization potential, and high stability of nitrogen. Other non-metal doping such as boron, carbon, fluorine, and sulfur are also found to shift the absorption band of titanium dioxide towards the visible region. Recent investigations revealed the fact that band gaps of anion-doped titanium dioxide are actually not narrowing, and the visible light absorption is resulting from the isolated impurity states located between the valence and conduction bands. For example, the isolated energy states created by boron is located 2.18 electron volt above the valence band. It's also reported that cationic sulfur doping creates an additional S3P level positioned 0.38 electron volt just above the valence band of titanium dioxide.